Hello everyone, this is Safa and welcome back. In the previous video, we learned how to analyze control systems using the Bode Plot and the Nyquist Plot. In this video, we will take one step forward by learning how to calculate the gain margin and the phase margin in MATLAB. These two stability margins are widely used to evaluate the robustness and stability of control systems. So let's begin. First, we clear the MATLAB environment. CLC clear closeout. This gives us a clean environment before starting the analysis. Next, we define the transfer function of the system. The numerator is equal to 100. The denominator represents the polynomial s squared plus 10s plus 100. Now we create the transfer function. The tf command creates a transfer function model and stores it in the variable g. Next, we display the transfer function. This allows us to verify the mathematical model before performing any analysis. Okay. Now let's plot the step response. First, we open a new window. The step command plots the step response of the system. Then we enable the grid and add a title and access labels. This provides a quick overview of the system's time domain behavior before moving to a frequency domain. Okay, now we generate the Bode plot with stability margins. The margin command automatically generates the Bode plot. In addition, MATLAB calculates the gain margin, the phase margin, and the corresponding crossover frequencies. This is one of the easiest ways to evaluate system stability in MATLAB. Okay. Here we calculate these values numerically. Here, MATLAB returns four important quantities. Gm is the gain margin, Pm is the phase margin, WCG is the gain crossover frequency, WCP is the phase crossover frequencies. Okay, then here we display these values in the command window. Displaying these values allows us to interpret the stability margin more easily. And finally, we generate the Nyquist plot. The Nyquist command plots the frequency response on the complex plane. This plot provides another perspective for evaluating system stability and complements the information obtained from the Bode plot. At this point, our code is complete. Okay, let's run the program and examine the result. Okay, first the transfer function here is displayed in the command window. This confirms that we are analyzing the correct second order system. And here figure. Okay, here we look at the step response. The output rises quickly, exhibits a small overshoot, and settles smoothly at its final value. This indicates that the system is stable. And here, let's examine the Bode plot. MATLAB automatically marks the crossover frequencies and computes the stability margins. From the command window, let's back here, we can see that phase margin is 90 degrees. This means the system has a comfortable, safely margin before becoming unstable due to additional phase lag. We also here observe that the gain margin is infinite. This indicates that increasing the system gain alone would not cause stability for this particular system. Okay. And finally, let's examine the Nyquist plot. The Nyquist curve does not encircle the critical point at -1 plus 0j. This observation is consistent with the large stability margins obtained from the Bode plot and confirms that the system is stable. In this video, we learn how to calculate the gain margin and the phase margin in MATLAB. We also interpreted this result using both the Bode plot and the Nyquist plot. Okay, that's it. Thanks you for watching. See you in the next lesson.